Welcome, everyone. Thank you for joining us for today's webinar. My name is Ismail Benayoun, and I am the US West Technical Director at Altair. Today is the second session of our webinar series on how to accelerate your electronics device design. So this webinar series is composed of two major tracks. The first one, the mechanical series, which will cover the broad scope of product design, from concept evaluation to manufacturing, going through some of the most complex simulation techniques and use cases. We will basically demonstrate how Altair Multiphysics platform offers the most comprehensive simulation and optimization solution in the market. The second track is actually the electromagnetic series. Our high-frequency EM experts will cover the topics of PCB design, verification up to manufacturing, antenna design process, their placement, performance evaluation, and optimization. And at last, we will show how to solve coexistence and interference issues between connected products, all using Altair's EDA and EM simulation platform. Both series will cover examples and models of various types. In fact, we will demonstrate the different solutions using various electronic devices, such as smart speakers, hand controller, Bluetooth mouse, and others. We will cover the various needs in product development cycles, from concept to reality with the analysis of components, sub-assemblies, systems, and systems of systems. In fewer words, we will share with you how Altair helps companies reduce time to market by enabling advanced simulation and optimization and machine learning, all leveraging one simulation platform. So today's webinar is all about multiphysics and lead time reduction. We will walk you through advanced and automated workflow designed to cover industry multiphysics use cases, all in one simulation platform with single model build for multiple attributes. Altair's strength resides in the combination of the advanced capabilities of its software and the engineers involved at our customer side, solving real-life problems. I wanted to share already an example with you here. Medical devices are modern and very complex electronics products, such as the injector developed here by Nolato. These products, when designed, they must withstand the structural and operational requirements associated with normal use, drop, misuse, all while balancing weight and cost consideration. So Altair Solutions enables simulation of structural, thermal, and fluid properties, vibration, electromagnetics, and manufacturing constraints in an integrated multiphysics environment. You have probably heard about Altair before. If not, please allow me to take 2 minutes of your time to tell you a little bit about us. Our vision guides our actions. We do our best to develop the cutting-edge technology that can transform customer decision-making with simulation, data analytics, and high-performance computing. With more than 11,000 customers around the globe, my 3,000 colleagues and I are located all over the world, developing and supporting more than 150 advanced software products. These products are the fundamentals of the broad solution portfolio we are offering to you, from design and modeling and visualization to multiphysics solvers to data analytics and high-performance cloud computing. While our roots are in the automotive industry when founded 35 years ago, we today develop solutions that are designed to deliver excellence across various industries. Here you can see some of our customers in each vertical and in the various industries. Now, without further ado, we will start today's topic and turn the time over to Ujjwal Patnaik, Our presenter today is actually Altair's Global Business Development and Strategy Manager for the structure. He has worked with multiphysics applications with our customers all over the world. To name a few, General Electric, Mazda, and Chevron. His various contributions to the SAE and NAFEMS conferences are focused and were focused and still focused on multiphysics problems across several industries. Ujjwal, the floor is yours.
Thank you. Let me share my screen here. Let me know if you see my screen, Ismail.
All good.
Thank you, Ismail. Good evening, good afternoon, and good morning to everyone who's tuned in to this webcast from your busy schedule. As Ismail went through the webinar webinar outline, here I'm presenting the multiphysics platform, which will support you in your electronic design and simulation. Now, but before we get onto the whole concept of design, simulation, and analysis, let's look at some of your key challenges. I think that's very important for us to recognize these. So in terms of multiphysics, I don't think any of us would want to just do a multiphysics analysis and say, here we are done. I think that's the beginning of your problem. That's the beginning of your design explorations. And also that's the beginning where you want to look at manufacturability and have ready design. That doesn't, multiphysics is not the end goal there. High learning expectations. When you're dealing with multiphysics, you're expected to catch up, learning and enabling yourself with adapting yourself with different GUIs or physics, which is not correct. Workflows. Now, workflows to help solve design problems, but you don't want to have workflows to connect different physics and tell you how to guide between two different GUIs. That's not the workflow you're looking at. And in the last, twice the cost for a single multiphysics answer. I think these should not be our challenges in order to go beyond and do multiphysics analysis. So how does these challenges are aligned with the outline what I am going through today? Let's see. Let me try and also maybe give you some benefits of it. First thing, Altair collaboration environment. And I will go through some multiphysics use cases. Now, collaboration environment is here, the objective is simulation-driven design. This has been our philosophy since 90s and also the foundation of the development. Similar multiphysics platform, which will be the broad spectrum of work you will be seeing in my live demo. It is a one user interface for all engineering disciplines. It has a live sync with CAD and built-in simulation workflows and automation enabled. OptiStruct single model multi-attribute workflow. I think this is what we are looking at, how it can reduce 30 to 70% of your time. Now, OptiStruct is one structural linear nonlinear analysis with optimization enabled, built-in multiphysics, and does not restrict a user to solve a single problem or a single solution in one model file. And that's the beauty of OptiStruct. We can discuss more about the benefits in the single model multi workflow. And the last thing is the license model in terms of the cost. But I would want to discuss this maybe as a follow-up, but I would rather take this time of yours to look at how we can go through the whole of this process of similar multiphysics and enabling it with OptiStruct single model multi workflow and looking at this using a speaker model for the live demo. Speaking about the simulation-driven design, which I mentioned, it's just not a philosophy. Let's look at Altair Virtual Product Development B. What you see on my screen, you have two V's. One is the simulation-driven design and the traditional design. Now, on the left side, you have a design, and the right side, you're going towards validation, and the bottom, you have it has two parts, design validation. upfront design changes with more freedom and start with a correct design. Now, simulation-driven design process, we have a shorter lead time. As you see, the V is much shorter. It will go through loops, unlike the old traditional method. This has been a part of our product development, which reflects on our products and platforms. So let me introduce you our platforms, Inspire and SimLab. Inspire is a design manufacturing process-based platform, while SimLab is a platform of physics-based environment. Now, if you look at these platforms, Inspire is applied early in the product design lifecycle. It accelerates, creates, optimizes through collaborations of manufacturing simulations. As you see on the Inspire window on the left here, you can see structural mechanics. You can see manufacturing, multi-body dynamics. Inspire is beautifully integrated with meshless structural analysis like SimSolid, dynamic motion simulation, and systems with motion solve, optimization with OptiStruct, and finally, auto polynerves for CAD-ready design. That's the platform of Inspire. While on the right side, SimLab is a platform very powerful as it's physics-based with structures, acoustics, fatigue, CFD, EMAC, and conjugate heat transfer kind of problems you can be solving with Altair solvers. And these two collaborate together in a common platform. As you see, it's a single collaboration platform environment where you have from the left to the right all various kinds of physics. Now, the design, and while designing any kind of a module of an electronic system, you have a wide range of problems you want to go before you hit all your KPIs in order to achieve those design attributes. Now, structural mechanics, multi-body dynamics, acoustics, flow, and electromagnetic. Now, if you look at this environment is enabled with high performance computation like HPC and GPU. This is critical for our multi-physics environment because you want to scale your problems, you want to solve them for various sensitivity analysis or optimization. Manufacturing is key after doing multi-physics analysis before you want to finalize your design and say, hey, this is the one I'm going forward for. So we enable manufacturing methods integrated in Inspire and SimLab in terms of injection molding, metal forming, extrusion, 3D printing, and casting. And also, after having a final design manufacturable or while doing the design between manufacturing and optimization, you also have a fatigue-enabled solution where we have fatigue life-based stress and strain. We can study weld fatigues, vibration fatigues, faster way of getting your designs validated in terms of their performance and durability. And then, of course, the optimization. This is an integrated platform, again, where you can do topology optimization, shape and size, and so on. This platform is enabled to collaborate beyond boundaries to reduce your lead times. It's interesting how we can plug and play all these together in a single environment in order to play with them at any point of time, do a structural analysis, follow the optimization, then do a fatigue, or in a different order, in any order you want to get onto it. Now, while talking about these environments of different physics, how about looking at some of the use cases here with respect to those physics? First one is a thermal FSI. Now, sorry, TFS applications, I picked a fingerprint scanner. It's like one of those security systems in biometrics. They used to unlock your areas, and they go through a lot of abuse of laws. Like they go to a lot of environments like hot and cold conditions, moisture, dust, and also it affects the operation of these fingerprint scanners. Here you see I have a CFD model which has an air domain, and then there's a structure of the PCB board connecting with certain cables around the fingerprint location where you want to scan it. Now, this goes through a CFD, hot and cold conditions, and followed by mechanical stresses in the end in order to calculate any kind of stresses for fatigue and various things. Now, CFD is carried by AccuSolve. OptiStruct is taking care of the structural side. Now, the TFSI is integration between structural mechanics and heat transfer application. Now, this here, it's an enabled, whether it's a unidirectional or bidirectional problem, depending upon the kind of problem you're solving. And there is a code coupling interface, which is automatically takes care of these mapping field entities. As you see heat flux and temperature and so on. User-defined field mapping is also enabled in the SimLab environment, where you can also decide how well you want to do it. So you have the at most automatic way and also a user-defined set pattern for yourself. Moving from thermal FSI, more getting into like a conjugate heat transfer, I wanted to elaborate a little more on the PCBs. Now you saw the injector, which Ismail showed in the initial slides. PCB is such a common thing used in every electronic devices like digital watch. You have washer dryers, you have fans, you have AC units. PCB design is there in every part of our life today. Electronic circuits, connecting electrical devices and also giving mechanical supports to these electronic components. That's PCB structure. Now here I have on my screen one such example of PCB, and you're seeing this PCB with temperature and velocities. Here, this geometry has two layers. Those experts on the call, you would know we have top and bottom. You have a copper, certain number of thickness, board material, FR4, and so on, where we are trying to solve a steady state laminar problem with components which heat dissipation boundary conditions. And we solve this with temperature and velocities, and then looking at the PCB overall on a steady state condition. Now, followed by this PCB goes through a certain set of mechanical strength tests. Okay? We would want to make sure that this pressures and temperatures which are dealt in the CFD bed is taken care as a preloading condition. And then excitation load is applied to calculate PSD stresses or any kind of fatigue studies have to be done on this PCB. It looks very small, has a complex system, and need a very good attention in terms of design KPIs from our side. Now, to generate any kind of such kind of use cases and workflows within SimLab environment, we have thermal flow and structural mechanics, where you can do coupling with fatigue. It could be unidirectional. The workflow in SimLab again is automatically taken care in mapping these entities from displacements and velocities, forces and temperatures on the other side, based on the right set of mapping parameters. And also the user has control in terms of the field mapping, how he wants to take it forward. Talking about electronics and not talking about e-motors. I mean, e-motors, again, in our modern life are extremely important. We have them in vacuum cleaners, dishwashers, computer printers, and fax machines, and also automobile systems. Electric motor here, you see, converts electric energy, mechanical, and most of these motors operate interacting between magnetic and electric currents. You will have a set of a detailed webinar on such design followed in this set. But here, what we're looking at is looking at your conjugate heat transfer. You'll want to look at any kind of these radiations which are coming due to magnetic and electric fields, studying the rotor construction in terms of the cooling area, cooling system, how this behavior of this motor is, or this design of this motor is taken care with such conditions or environments. Here we have AccuSolve and Flux are prominent tools out there, solvers out there, where you can do unidirectional workflows again in SimLab, automatically taken care for this mapping between Flux and AccuSolve. As you can see, the mapping entities could be like power densities to temperatures, could be 2D, 3D environments from the CFD, from the electromagnetic to the CFD. And also these mapping entities are optional if user would like to try to intervene and make a user setting based on mapping. Electric motors also are a little complex because we would like to look at the acoustic side of it. Now you can see here on the left side of the screen, I have electromagnetic forces from Flux. Again, the EMAC Flux, and we would like to study the noise. We want to predict the noise at different RPMs. It's a complex in terms of electromagnetic and acoustics, but here in SimLab, it gives us this platform to look at those efficient way of making sure the pretension bolts are applied on these motors. Getting those excited forces, electromagnetic forces as excitation points for the structural point of view to conduct any kind of harmonics analysis. Then we would want to look at various speeds and also want to measure sound pressure levels at a distance around the environment. With infinite elements technology in OptiStruct, you have this electric motor inside this infinite element structure, where will also be a part of our demo today. You can steady sound pressure levels at any distance. Now here, we're talking about EMAC, and we're talking about structural mechanics. We're talking about field mapping of loads to forces, which is coming to OptiStruct. And then you have this whole platform built for us to solve and look at the KPI parameters for sound pressure levels. So it's nicely conjugate heat transfer kind of problems, and also acoustic kind of problems for the motor design, which is very prime from the structural point of view. Couple solutions will not be completed if we don't talk about CFD and MBD. Now here, I'm looking at a washer. It's a maybe washer. The client here has a balance ring. It's a ring which is fitted here, and this is the drum and the bucket rotation. There's a wobbling effect. Now this balancing is very interesting for this maybe design, where you have this fluid filled ring at the top of the tub. As the load shifted the washer, the load may become more concentrated. One side of the basket, fluid in the balance ring shifts it to the opposite side. Beautifully engineered, where you look at the load to help the offset of the weight and keep the rotation of the basket stable. I think that's the overall use case where we would like to solve. Now here with MBD, motion solve, and IQ solve interface coupling, in terms of the code coupling interface, we can actually solve such problems where you have the mapping between the fields of forces taken into accountability, integrated with displacements and velocities on AccuSolve, and solving such problems. Now this is, again, this washer and dryer could be having a PCB, it could be having it has a motor, it has various components, what we just went through. So in your ecosystem of solving an electronic design, you want all these different physics to be taken care in the order of the fashion you want, with the end criteria of making sure that you meet and match your design KPIs. Here is a summary of what we just looked at in terms of our physics, multi-physics solutions enabled in an optimization platform under SimLab and Inspire. Moving on to the next section, other than understanding the collaboration tools and the platforms of Inspire and SimLab, I think we should now look at the single model multi-attribute workflow of OptiStruct. Now, jumping onto such workflow, I think it's easier to map it to something where you deal with today in your design groups, simulation groups. Now, if you look at, I would want to take speaker example in terms of the engineering product design groups. We have your key performance indicators for design and analysis. This is one such chart where you have a speaker design, you have all of them together in terms of quality and design and then improvements, correct? Even though we have a single CAD, we are looking at creating various set of models for each of these simulations. Not good, but let's leave it at the but, come back to our single model multi-attributes and look at how this is enabled. So here today, my goal is to look at a good design for a speaker. That's the objective. But in order to make a good design, nobody likes to design bad design. For a good design, I would want to look at various parameters put together. If I check them off, not only should they efficiently be effective to make sure they are solved for a good vibration, good thermal, and making sure they take all the abusive loads in day-to-day life, and also electromagnetic effects, and then make sure the design is good. That is how I would want to pass my design for the speaker and say, okay, this is ready to manufacture and go out for the market. But inside the CAE group, you would want to, you look at these various physics. So today, I would do something in terms of vibrations. I want to touch upon thermal. I want to touch upon the strength analysis and a drop analysis. And there is another segment of this in-depth detailed jump into vibroacoustics, where my colleague Ismail would jump onto this topic, which needs more attention on the 28th of July as a part of the second webinar of this session, what we're doing here today. So, but I would touch upon the rest of the items, what you see on my screen here. We spoke about the workflows. Now, we are used to model per physics, as I mentioned before. Is that what you do today? what's the common or typical scenarios of your framework? Are you building separate models for each of these analysis? Is your workflow time consuming? If you do it this way, of course. And do you solve all of them in different solvers? And do you struggle converting these models from solver A to solver B to solver C and so on? Wide range of design needs and product design cycles have to go through. You want to make sure that these are done in a single set. And again, when you have optimization to make sure all these KPIs are taken care across these analysis, it's a further challenge. So we are saying that in this current process, when you deal with different solvers or different engines where you're running these problems, you could run into challenges in terms of errors in the models or challenges in terms of larger lead times. Now, with a single model multi-attribute workflow, what we are talking here is we're looking at solving major number of your structural problems within one solver. Now, not by solving these in one solver as multiple model files. We're talking about making sure we stick to the single CAD, what you got, and trying to stick to that environment of the CAD while making all these designs and also working in the multi-physics environment. So if you begin with a single CAD assembly, automated meshing process without any cleanup in a SimLab environment. And if you're beginning with an FE model, fine. SimLab can facilitate comprehensive analysis from a different solver getting into OptiStruct and make sure you're enabled to do something like this. So model handling across various groups can be taken care, and you can nicely look at this whole set of different analysis in a single environment. So single model management in SimLab allows you to solve multiple physics in OptiStruct. These are enabled again for optimization or fatigue studies, as you will see in my demo. So here with this process, we are saying that you would not have any challenges to do with model conversions or error-prone situations where you'll construct the model as it is, not making any lot of assumptions or considerations to reduce your model into a certain set, making sure you have a single model to run in a single solver. This is one of the processes which has been taken at the customer side. Today, this process is in place and people are using this, and this is at one customer side. I'm deviating a bit from the speaker, but just showing you an example of the power of single model multi-attribute, where a customer without a single model multi-attribute has 3 hours in meshing time, and he spends about 5.5 hours to set up the model for different analysis here. So he has a different mesh which has to be taken care, and then for strength, he's making sure that he has a similar mesh setup, and then setting up for strength analysis is different. So you have 2 different models, again, already, and trying to do a durability analysis, which is your final goal. So you are spending this time, about 15 hours, to go through this whole thing. Mapped process for a vehicle subassembly. Now, with respect to using the single model multi-attribute, we are saying that you can do this same meshing. You can set up the model for dynamic stiffness, strength, durability, and optimization within the 6 hours of your time and have a single answer there. Now, this is the approach. You can actually save about 3 hours or 6 hours of your time. That is about 40% faster with respect to your existing process. I don't think there is a tool out there which can solve multiple solutions in a single model, multiple different physics in a single model, the way we do it in OptiStruct. With mapping this same thing with our speaker model, I think that's interesting how we want to look at this with respect to those analyses which I just showed you before. Now, I'm challenging myself here with the CFD, the TFSI analysis. I'm challenging here myself doing a nonlinear analysis, and also the final goal for us to do any kind of acoustic analysis in this particular model. Now, if you look at this in a typical scenario, without even talking about single model multi-attribute approach in SimLab, I would have a CFD user in a different GUI. I would have a structural engineer in a different GUI, could be a different user again, and then the vibroacoustics could be a same GUI or different GUI depending upon how you're doing it today. Now, looking at the number of hours you spend in the meshing and the model setup for each of these analyses, finally, you're looking at the total answer and looking at 10 hours per design Now, this is only the model setup. We're not talking about any solver time here. Bear with me. In the single model multi-attributes, I am saying that we can do TFSI, nonlinear static, structural vibration, and vibroacoustics in this process. Now, how many hours it's going to take? We'll take a look at that. The second part of this webinar, and I'm talking about a live demo where we're looking at a speaker model. Now, we're talking about, like when I talk about a speaker model, we should look at how the evolution of speakers are. I think the scientist from Edinburgh, Alexander Graham Bell, invented the first loudspeaker. I think credit to him, we're talking about this loudspeaker. Now, looking at the speaker, I think it's a device where we would like to look at amplify the sound or listen to the sound. I think that's the goal, what he had to derive it. But now if you see the speaker's evolution on the left side, they become more fancier, more complex, more aesthetic. I think, and also the great quality of acoustics are being generated various of these set of speakers. Now, having said about that, let's move on to the speaker, which is built in using a stiff paper cone, a coil of thin copper wire. This is the cabinet, what you look at, what you're seeing here, and it has a cone, copper wire, it has magnets, usually mounted on that, and also this coil on the copper wire moves back and forth. Henceforth, you see the electric signal which is passing through. As you see on the back side, there's a PCB board out there. Now that's the magnet, and then you're looking at the paper out there. And this is the PCB, and there is a fan. So speaker itself is a complex system. This is there as part of every household. This is sitting beside you on your couches, in your bedrooms, in your living rooms, or anywhere else. And this has a mammoth of things inside it, and complex designs like PCBs, and making sure you have a CFD mesh, making sure you have a PCB mesh or use acoustic mesh or a structural mesh is not easy. It also has heat exchangers. So you're looking at thermal application, you're looking at acoustic port. So these are all various parts of my speaker, what I have for you today. If you look at it, all these parts are connected with certain set of assembly patterns and also disconnected based on certain context elements which are defined. Now, how do we look at this particular speaker model with respect to our workflow? Now here, let's look at the first set. Welcome to SimLab workflow. Now, on the left side, I have the loudspeaker management where we would want to look at the structure, the fluid mesh. We would want to look at all these parts which I just mentioned, and also maybe the material properties. So let's look at the first part of a quick demo for me to look at these things. I'm clicking on my video here. So you should be seeing a video which is being played now. And here on, if you're seeing SimLab for the first time, to that user who just asked me the question, you have ribbons on the top, and you have all of these ribbons coming based on a certain number of entities which are picked. Like you have assembly, you have analysis, you have results. So they go in the flow where you get a geometry. In SimLab, there is no geometry cleanup. Sorry, I think that's the best way you can tell a user that you get your geometry, and SimLab does very well. Without any cleanup, it can give you a good quality mesh. Now, after making sure the assembly is set and you have all those patterns, now here you're looking at the left side is a model browser. So I have two sets of models for this particular simulation, and one is the structural assembly and another one is the CFD. The common parts are there between both of them, and the non-common ones are the ones which needed more attention in terms of the mesh. Now you saw that that was the acoustic ball and the plotted elements. Now we'll come to that. Now let's look at the CFD. Now in this particular CFD, you have the speaker CFD, and you have the cabinet, you have the heat exchanger, and you have the fan and the woofer and so on. So if you look at this particular CFD model, the details, there is a fluid mesh inside it. You have a fluid mesh, which is making sure we have the boundary layers, and it also, all these elements in the CFD are meshed. Now, let's zoom in to look at the structural mesh out there. And you can see this is a construction in a cut section, and you have the PCB board in the end, you have the microphone speaker in the front, top and the bottom, and the cabinet in the green. Now, in the CFD, the expert sitting in this call would know that you would want to look at certain number of boundary layers between the parts. And these have to be assigned uniformly, taken care at every part in the CFD side. I think this is the critical thing. Now, SimLab is just not a meshing tool for structures. It can take care of very well in terms of CFD meshing pretty nicely. And I think it does a great job in setting up your CFD models for your CFD simulations. Now, with saying so much in terms of the CFD, again, defining these inlets, outlets, making sure these boundary layers are assigned, setting up these CMD in terms of their materials and properties are also very nicely done. Now let's look at, before we get on to the material side, let's look at the structure part. Now this structure has a acoustic domain where we're trying to look at the sound pressures measured at these response surfaces. Those are the plates which we put it in part of the room where you're measuring the speaker particularly in your living room, and to see how the acoustics are traveling at a certain distance. They are placed at a certain distance, and those are our points what we're looking at. Now in the structure part, you have another fluid domain. In the structure part, irrespective of the structural parts you have, make sure that you have certain number of layers across the thickness. You also need the fluid so that you can do a certain acoustic analysis. I think that's the beauty in SimLab in the model management. It can have a various mesh exist, connecting or disconnecting depending upon the kind of simulations you're doing, and it will allow the user to play around and make sure you submit certain jobs and the coupling happens pretty much between both of them. Now what you see here is the acoustic mesh, and you see again the cabinet, and these are the number of layers. SimLab, while OptiStruct is taking care of all the best practice of the solver, SimLab is taking care of the best practices in terms of the meshes. So for the acoustic, you want to look at how these meshes are taken care in order to get the quality of the sound wave length to be traveled. Number of layers, at least 4, is taken care in SimLab. So that's what SimLab does while creating this whole globe, whole sphere model for yourself, model for the cabinet. Those guidelines are in place for you. So all you need to do is make sure that you click a sphere, pick the model, and then say, I want acoustic mesh inside that particular part. Now, the last part is getting into the materials of it, which will allow the user to define a common material system for structure, CFD, and EMAC. If you see here on my screen, on the material browser part, I have a solid and I have and properties. In the solids, I have all the structural parts, and in the bottom, I have fluids. So there is a different shade, but the solids are part of the CFD analysis, and also the air are part of the structure analysis also. So nicely, these parts can be defined in terms of materials. Now, you can also get this from your database, which is coming through, and you can read that in SimLab pretty nicely. And then once you have that in, you can then set up your model for the next setup. So that is what I have in terms of just making sure you have the mesh generation for structural and CFD. You have the model materials and the CFD materials and properties defined for structural and CFD in the same system. And assigning them is very nicely done in SimLab, where you have it is enabled in the browser, and also it is enabled on the screen itself, where you can just go onto the screen, right click, pick a part, and say, I want to assign this particular certain material and so on. So it's nicely done, easily enabled, and organically, thoughtfully taken care. Moving from setting up the model in terms of meshing, now we want to get into anything in terms of definitions of the parts between. So let's look at the set of use cases we are going to solve, right? One is the thermal FSI, where you have the thermal flow analysis, you have fluid material, those things you just saw in terms of defining, and also the inlet and outlet definitions, and also the fan cooling. We will look at how these things are done on the CFD side. Make sure we have about 25 parts and 4 different load cases we're looking at. We're also looking at nonlinear static analysis, followed by a TFSI analysis. We're looking at all these pressures and temperatures to be mapped nicely on the structural mesh in order for us to conduct any kind of preloading, followed by nonlinear large displacement analysis, which has contacts and so on. And the last thing is in terms of the drop analysis, where you have the same mesh taken care, and then assigning this speaker model, which is being abused, which is dropped into different various kind of angles, faces, or edges. Now, again, this is an explicit analysis which can be done and you can make sure that this use case also being checked off in terms of APIs to see how these connection points are taken care of while you go through any kind of drop analysis. Now, while we spoke about nonlinear, while we spoke about drop, it brings us to the point where we want to look at how contacts are defined and how we want to do, how we want to replace various set of parts coming in and going based on CFD or structure analysis. Without wasting any more time, in the model setup, let's look at contacts. While looking at the context definition here, I would also want to bring you to the attention where we saw the model browser. Now here is the solution browser. In the tabs in the bottom, you can drag onto and you can look at the solution browser where all the solutions are set based on the type of analysis you're doing. And on the top in the solutions, you can pick between different solutions. Now, I will go into little more details of that in the next set of demo, but here, let's look at how these contacts are taken care of. Now, here in this particular demo, we are looking at the contact definitions and how this SimLab takes care, understands these geometries, NURBS in terms of identifying these cylindrical parts, identifying these fillets, identifying these flat surfaces, and detecting these contacts pretty nicely, and solving for any kind of setting up any kind of contacts is so easy. Now, here is a quick shot of picking contacts, and in this on the window you can see I'm doing an auto contact, and I'm making sure I pick all the parts in this particular assembly in the structural side, and I have all these parts displayed, and I click OK, and based on the parameters set in terms of tolerances, it will go and find all the contacts, respective contacts in the field. Now, once these contacts are defined at the set where I have on the global settings. Now, you in the electronic side, again, you may have certain contacts you want to be setting a certain analysis, and you want to take it off from a certain analysis. You may not have all the contacts in every analysis. I think the good thing about it is, other than looking at these contacts at the global level, you may also want to enable and disable these contacts. Now, here is a panel where you see I want to pick A, B, C contacts for this analysis, and I don't want these contacts to be part, or I want a different kind of friction coming in different contacts. So those things are beautifully engaged within SimLab, and OptiStruct tends to take care of those settings in terms of how these contact definitions come and go, and you can have them taken care while type of analysis, not worrying about where it is coming from and how these things are done. Now, other than setting these contacts, it's very important for us to look at any kind of part replacements. Now, I'm turning off the contacts here and making sure these contacts, these parts, like this particular magnet part which you see here, I want to have a replacement. I take the liberty of just taking same magnet with a different remesh, but you can have a different magnet or a different part coming in. For the demo, I have these two different magnets. Now, it's important when you go through this whole challenge of creating contacts and materials and definitions and meshes all, but it's a shame when you want to replace these parts, those boundary conditions don't come through. But I think in SimLab, beautifully, you can see I have replaced bodies, and I can actually go there and I can pick the part, and I can say, okay, I want to replace this magnet 2 with this magnet new, and it will recognize what all the entities of the FE mesh and FE modeling are already in place, and then nicely moves it to the new part without taking care of all those, updating the new contact groups, updating the new materials, updating the new parts, and making sure those are enabled for you for analysis ready. Now, moving from the part, let's look at the next set of analysis before I go and do the complete analysis setup and look at the results. Now, in terms of the set of other analysis which we wanted to look at, we wanted to do dynamic analysis like normal modes, where I would like to recognize the structural parts and structural modes and rigid body modes and make sure those are aligned with my constructions. And also, I would want to look at acoustics. I want to measure sound pressure levels at a far field. I have this speaker which is excited. It has all kind of preloading parts which is coming from, whether it is a nonlinear or whether it is coming from a TFSI. Those things are set because we want, this is the final answer. We would want to know if the acoustics, the sound is important for us in the speaker design. So keeping that as a goal, now let's look at the solution management. For the solution management, I think it's good time for us now to look at the solution browser. So without wasting much time, let's look at in the solution manager, solution browser, how we can set these various different kind of analysis and look at each of these setups for whether it is CFD or whether it is the structured enabled for us. Now, if you see this particular screen, you have a solutions enabled. When you click on a structure, automatically the structural BCs, structural boundary conditions are enabled in the panel itself. Now, the moment I click on thermal, you will see that boundary conditions changing and so on. Here, I'm saying I want to do a structural solution. There are a set of structural analysis and solutions which are enabled in SimLab based on the set of analysis you want to do. And similarly, if you want to do a flow, there are certain set of analysis in CFD and thermal and so on. Now, at the beginning in the solution browser, you have a CFD, you have a structural nonlinear analysis followed by acoustics and so on. Now, while doing these analysis, it's very important for us to look at the CAD parts, the parts which are assemblies in the model. So here is the trick where we tend to pick the parts which are associated for a certain set of analysis. Now, looking at the CFD side, I think look in this particular transparent view, you can see the bodies which are associated for the CFD. So the fluid mesh which is inside and all the parts, including the fan and all those locations, are taken care for, which are very much important for us in the CFD kind of an environment. Now, in the CFD analysis, now let's I can jump there. So now in the CFD, it is very important for us to look at the initial conditions where I'm looking at the temperatures and pressures. I would like to look at the boundary conditions where I'm looking at say the heat power source, and also I would want to look at, other than the power supply, I want to look at the magnetic locations, and also I would want to look at any kind of definitions where I want to have this matching mesh and the convection definitions on the fan and the fan volumes which are defined, so that is enabled, because when the fan is rotating, we want to look at the mesh technology which is incorporated, which enables the fan motion and so on. After setting up these boundary conditions on the CFD, also the CFD parameters. The moment in SimLab you tend to activate any kind of structural CFD analysis, the parameters are automatically set. I've just opened one of the panel. You can see the defaults in terms of the turbulence analysis or the conjugate heat transfer setup is it's all enabled out there. All I'm trying to do is a quick review of how these things are set. If you want to make additional changes to that, you're most welcome to make those modifications in terms of number of time steps or a certain turbulence method or a certain governing equation. You can also make those changes for yourself. Now, on the structure side, similarly, these are the parts which are part of the structure analysis. Now, you can see in SimLab, the structural part is enabled. So that is why you see the dark one. And once the CFD is enabled, that will tell you which part in the solver browser are you working on. Now, in the solution browser, you also have the FE bodies, which are part of the whole ecosystem of the structures. And also you have certain global settings, and then you have certain local settings for each of these analysis. Now, in terms of the structure, these are the global parameters which are set for all type of analysis which are included in the OptiStruct. So this is the nonlinear, the acoustics, and the normal mode analysis, where I'm saying this is a single model, what we are working within the OptiStruct of the single model multi-attribute. I also have output controls request, and I also have constraints and so on. The good part about SimLab, once you start setting up these models, anything definition is not enabled, it will never allow you to run the model itself. Those are the defaults which it needs from the user to be incorporated. So here you can see the boundary conditions. For nonlinear analysis, that is a must. For modal analysis, that's an optional, because it may think that you're doing a free analysis versus a constrained set vibration analysis there. So these are pretty nicely included. Now, once you have the CFD analysis done, and then you want to do nonlinear analysis in SimLab, if you're doing a sequential coupling, it enables you to pick and say, hey, I want to take the temperatures mapped onto my structured mesh. I want to include pressures from the CFD analysis to my structured mesh. Those are taken as a preloading, or those could be taken as loads to solve any kind of analysis. Now, this is pretty much done in SimLab pretty nicely automatically. where the user does not have to worry about whether he has a mesh correct, is it different geometries, is the CAD okay, what are the coordinates. These things are pretty nicely handled at the CAD level because you're dealing with a single common CAD. Only thing is you're dealing with is a different mesh. Now, other than setting a CFD, setting a structure analysis, you can also do a couple of other things which I've raised in the first in terms of key challenges. Now, irrespective of doing CFD and TFSI, you can also do certain set of optimization analysis, or you can also do certain kind of fatigue analysis in the same environment. You can just keep adding the set of solutions in the same browser here, in the SimLab, in the solution browser here. So here is one quick set where I said, I want to just handle and I want to do a sensitivity analysis only with temperatures coming from CFD, or I want to do only with temperature study. I want to do a fatigue life study based on that, and so on. So these things are nicely thoughtful, and then these things are enabled out for you there. Now, once I have the structured model set up, the CFD model set up, I set the model up for running. And once I have these models run, I want to look at the post-processing. Now, it's very interesting that in SimLab, the unit system taken care, the job submission, just a click. If you have an HPC, you can integrate that HPC. It's a matter of enabling it with a short command out there. And then once you have those results running on your server or your desktop, now you look at the whole GUI where you're looking at some results. Now, in SimLab, not only you can do a CFD meshing, you can do a structured mesh, of course, but you can also handle these results entities from whether it is a CFD analysis or an acoustic analysis or a dynamic analysis or nonlinear analysis in a single window. Now, this single GUI will enable you to look at results, diagnostic these results together in a single shot, and these are something templarized. So you can create those solutions, what you have previously, which I showed you, as a template for you to save it. And also in terms of getting your results, you can also conduct DOE studies by changing parameters like thicknesses and materials and geometries coming from your CAD sync in SimLab. All of this physics in a single GUI, including optimization, is what you can do in the SimLab environment. Now here on this chart, you can see in the bottom, I have sound pressure levels, which is calculated. This is the pressure plottable elements, which you can see at a particular frequency, which is the peak frequency. And you can look at how the sound pressure levels are there. And on the left side, you can see the nonlinear stress analysis, what you're actually looking at displacements here, how those are constructed and looked at large displacement nonlinear analysis. And at the top, you have the CFD. It's a plot where you're looking at pressure or temperatures. And on the right side, I can actually look at eigenmodes. So some of these analyses are transient, some of these analyses are frequency dependent, but I think in SimLab beautifully, you can enable them based on the type of type of simulation you are and the construction you are. You can look at these results at the same point. Now, having looked at the meshing, the model setup, the workflow in terms of OptiStruct single model multi-attribute, I think it's a good time to look at the slide which I challenged myself in terms of how many hours we take to set up this whole thing and run these analysis. Now, I think if just to remind you, we said we take about 10 hours to set up this model, and now I'm looking at about 3 hours with SimLab and about 70% faster than the time. Now, in terms of key takeaways, Altair platform is truly a collaborated environment, as mentioned before. In this collaborated environment, you have SimLab multi-physics platform, which enables to do design studies, optimization, fatigue, and all. And also the single model multi-attribute sets you up straight. With this particular example, we saw 70% time reduction. I did mention about the cost of these of Altair licensing. We would definitely want to talk to you about it at some point. Reach out to us separately. We would want to look at how you can make sure you have a multi-physics solution at a single solver cost, not twice, unlike the others out there.